Here's a question students almost always get wrong the first time. If I start with a carbon atom and I randomly add 4 groups around that carbon atom in no particular order, how many unique versions of this molecule can I make with these colors? The answer is not 8, it's not 16. Make your guess during the intro, and I'll come back and explain why the answer might surprise you. Hey there, ninjas. Today, we're talking about stereochemistry, which really boils down to one idea. Molecules are three-dimensional, and not all three-dimensional arrangements of atoms are the same. If you can hang on to that idea, everything after that, chirality, enantiomers, RNS nomenclature, becomes so much easier. In this video, we're not going to name anything. We're not going to assign any labels. We're just going to wrestle with one question. What is stereochemistry and chirality? And the way we're going to get there is by coming back to our thought experiment. How many ways are there to arrange 4 unique groups around a carbon atom? Let's start by imagining a carbon atom. And that carbon atom has 4 different groups attached around it. Doesn't matter what element or how big or complicated those groups are, so let's just abstract them into 4 different colors. Before we build anything, did you stop and make a guess? How many unique arrangements of 4 different colors are there around a carbon atom? Let's start answering that question by addressing one of the biggest misconceptions when it comes to organic chemistry and carbon. Even though we often draw Lewis dot structures with bonds like this, the carbon atom at the center is not square planar. All 5 of these atoms with the carbon are not coplanar in the same plane in a flat screen. The carbon atom is tetrahedral. Because carbon is sp3 hybridized when it has 4 bonds around it, the carbon is tetrahedral. We can have at most 2 of those bonds be in the same plane as the carbon. And to complete the tetrahedral geometry, one of the remaining bonds needs to stick towards you as the viewer, and one needs to point away from you as the viewer. The wedge bond indicates a group coming towards you out of the plane of the screen towards you as a viewer, and the dash bond indicates a group going into the plane of the screen away from you as a viewer. Let's add these groups one at a time around our tetrahedron. We'll start with one group, let's say the yellow group, and let's put it anywhere on this tetrahedron that we want. It might seem like we could have one of 4 possible choices of where we want to put that yellow group, but because molecules are three-dimensional and we can rotate them in space, we can always rotate that group such that it is down on the left side of the in-the-plane bond in our tetrahedron. No matter where we put that first group, the yellow group can always be rotated to be down on the left side of the in-the-plane bond. Now we can add the second group. Let's add the blue group next. Again, it seems like there are a lot of choices of where I can add the blue group, but no matter where I add the blue group, I can always rotate around the single bond to put the blue group in the plane on the right side of the carbon atom. Again, it seemed like there were multiple choices, but rotation allows us to standardize the molecule. And this is a key idea in the concept of stereochemistry. Rotation does not make a new molecule. Now something changes. When we place the third group, either on the wedge bond or the dash bond, we've made a real unique choice. Choosing the position of the third group forces the position of the fourth group. There are no more choices. Had we done the opposite, no matter where we place the first group, we can always rotate the model to have that first group on the bottom left side of the in-the-plane bond. The second group, no matter where we put it, can always be rotated down to the bottom right side of the in-the-plane bond. By placing the third group, I make the first unique choice for this molecule. Putting the third group on the back carbon this time forces our fourth group to end up on the wedge bond in our structure. No matter how you build the molecule, by putting yellow on the bottom left, blue on the bottom right, you will always be able to find one of 2 possible orientations. So the answer is 2. There are only 2 unique ways to organize 4 different groups around a tetrahedron. This isn't memorization. It's geometry. By the way, if you like the model kit that I have, it's my favorite model kit for organic chemistry. I have a link in the description down below where you can get one. When a carbon atom has 4 unique groups around it, we call that carbon chiral. Each of these carbons is a chiral center. The word chiral derives from the Greek, which means handedness. It's a pretty good analogy to call these 2 molecules different hands of the same structure. One of them we would consider like the right-handed version, and the other we consider the left-handed version. Any sp3 hybridized carbon with 4 unique groups around it is a chiral center. There are certainly other examples of stereochemistry than chiral centers, but this is the most common in undergraduate organic chemistry, and this is the one we're going to talk about the most right here. These carbon atoms have a special name because they have 4 unique groups around them. We also have a special name for the relationship between these 2 molecules. And let's be clear, these are 2 different unique molecules. They have the same 4 groups around the central carbon, but if you take one in some random orientation and some other in some other random orientation and you try to line them up, there's no way to line up all 4 groups. two of them will always be mismatched. These are unique structures. And when we have a molecule with a chiral center and two versions of that molecule that are not superimposable, we call the relationship between these two molecules enantiomers. Enantiomers is derived from the Greek enantios, meaning opposite, and mer, meaning part, opposite part. You cannot rotate one enantiomer into being the same as the other. No amount of flipping or spinning or manipulating them in space will turn one into the same version as the other. The only way to convert one into the other would be to break the bonds. And now we're doing chemistry, not manipulation. This is the foundation of stereochemistry. Stereo, think left and right. Stereochemistry is when we have two molecules with the same connectivity that only differ in their three-dimensional arrangement in space. In this core fact, there's only two unique ways to organize four different groups around a tetrahedron, is the foundation of all of stereochemistry. From here on out, everything that you learn, RNS orientation, optical activity, reactions that produce chiral centers as product, all build from this basic idea. If this finally made stereochemistry feel logical and not mystical, you're exactly where you need to be. In the next video, we'll learn how to take these two stereocenters and label them as either R or S, step by step, with no memorization or shortcut. I'll see you in the next video, ninjas.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.